Noel. Let's see how many we got. Let's give it 2 minutes before we get started. Wait for a couple more people to show up. Just sit tight for 2 minutes. I realize that when I'm giving the class some time here, I should be pausing the recording. Otherwise, somebody watching this afterwards is going to sit there for 2 minutes. So how do I do that? Recording. Awesome. Okay, let's get started. Sorry about having to cancel things last Thursday. Couple of things, I'll just let you all know what's going on. On Wednesday morning, I got a call from people up in Portland, Oregon, where my son was living, saying he had to go into the hospital that day. So I got on a plane Wednesday afternoon and flew up to Portland, which is where I am right now. Actually, he's doing okay. He's fine, but he's going to be released this afternoon from the hospital. So just a warning: I may have to end class abruptly if I get calls. And if that happens, Julie Madera is also already given this lecture, and she's posted it as well. So if I have to cut this short, I'll just link her video to on the webpage, so you'll be able to just watch the rest of this. Whatever I don't get to, you'll be able to watch. And she's actually done a smart thing. She took this lecture and broke it up into 3 little chunks. So there's actually 3 videos on her webpage where she discusses all the things we're going to talk about today. And that's kind of nice, so you don't have to do it all in one sitting. The other thing is, because I'm here dealing with hospital stuff and things like that, I've had a lot less time for email. And in fact, even leading up to this over the last 2-3 weeks, I know a lot of people have emailed me with, especially since the coronavirus shutdown started, with issues on Gradescope, and there's 50 of you. It's been a little hard for me to keep up on that, and I don't have Grooters to help right now. So I'll just say this: if you have been, a lot of the things people have emailed me about is just problems submitting things to Gradescope, or maybe you missed a deadline. I'm going to be very lenient now with deadlines, so don't worry about if you're late. And if you can't submit it through Gradescope, just email it to me. So I know a couple people even this morning emailed me saying they missed the deadline for problem 10.3. So just email it to me, okay? You don't have to worry about it. And if I get a chance, I'll send a confirmation email saying I got it, but chances are I probably got it. If it's that sort of thing, I wouldn't worry about it too much. Or another thing, if you worked with somebody else and you have the exact same code as them, and theirs was working but yours wasn't, don't worry about it too much. Maybe shoot me a quick email saying that, and I'll just respond saying that's fine. I'll give you credit then. So that sort of thing. I'm sorry again. I'm sorry I haven't been so responsive as I should be, but we'll get it all sorted out. Okay. All right. Let's get started on today's material. First thing, we'll just spend 2 slides or so talking about the extra credit problem, which is this famous read it and weep sequence. So this sequence here, you'll see on the left there, it starts with 1, and then 1 1, and then 2 1, and then 1 2 1 1, and then 1 1 1 2 2 1. It's a very mysterious sequence, and I know when first time I saw it, I stared at it for a while, and I couldn't figure out what the pattern was there. And the title of this slide is really tells you what the pattern is. At least the first 2 words, the read it part. It's a cool sequence. So each number in this sequence you get from the previous number literally just by reading it out loud in English. So you start out with 1. Nothing mysterious about that. It's just the beginning of the sequence. Okay, and then when I read the number 1, I read 1 1s. So the 1 1 in the second entry there means there's one number 1. So this is the number of this digit that I just read, okay? All right, now to get this one here, well, the previous one had 2 1s. So this is the number, this right here is the number of numerals 1 in the previous one. There are two of them. There are two ones in the previous one. Okay, but then if I read 2, 1, I'm reading only one number 2 and then one number 1 when I read the previous one. There's 1, 2 there, and there's 1, 1 there. 1, 2, 1, 1. And then when I read that, I just read out 1, 1. There's 1, 1. That's this. This is 1, 1. There's only one number 1. Okay. Then there's 1 number 2. There's the 2. And then there are 2 1s. Right? That's these two. Hope that's clear. And then the next one, well, there are 3. In the next one, there are 3 1s, and then 2 2s, and then 1 1 in the previous one. Right? So you just literally read the previous one out loud and then keep track of how many 1s there are, how many 2s there are, how many 1s there are, how many 3s there are, etc. It's kind of a amazing, mysterious sequence. And the shocking thing about it is that there are patterns in this sequence. It's not completely random, and in fact, actually, it is asymptotically this exponential constant. And there's even some patterns there that when you start plotting these things, you can see these numerical patterns, and these numerical patterns are related to some very high degree polynomial, which was discovered by John Conway. And I want to say a couple things about John Conway. Actually, we're going to spend a lot of today talking about another invention of John Conway's, which is called The Game of Life, which is one of your homework assignments. And it's a little bit ironic that Conway is coming up today because just a few days ago, his death was announced. It's extremely sad. He was a monumental figure in mathematics. I know many, many, many mathematicians who became mathematicians because they were inspired by John Conway's work. He was in his 80s. Last time I saw him in person was about 5, 6 years ago, and he was an elderly man who's he's a character. He's a crazy character. I've talked about him in class before. I don't know if you all remember when I talked about how you can count on your hands in binary 1, 2, 3, 4, 5, 6. And I told the story about John Conway and how he was known to give lectures while he counted his footsteps while he was lecturing. It's just there's millions and millions of little stories about him. I was at a conference once with him and went out to dinner with him and a group of people, and he had this plastic shopping bag. He looked like this sort of old grizzled man, and he looked a lot like a homeless man, to be honest. He's always kind of disheveled, has a big gray beard, and he had this plastic shopping bag with him. And he pulls out of this shopping bag all these like math toys that he invented and sort of passing around the table. And it was like the most lively, interesting conversation about all these different things. So I don't know, I could go on literally for hours talking about John Conway, and I'm incredibly sad right now because he just passed away. And he passed away from the coronavirus. He became infected and passed away, but he wasn't an elderly gentleman. I realized just now I don't have the chat window up, so I don't know if anybody's saying anything. No, okay, there we go. All right, so this is your just one of the homework problems. If it's an extra credit homework problem, just do it if you have time. If it seems fun to you, I wouldn't spend a lot of time on it. But it is an interesting and kind of a fun problem to think about how you would do this programmatically. All right, today we're going to talk about a couple of different topics. One of the topics we're going to talk about is a really important concept in programming, and that is whether or not data types are mutable and how those data types are stored in the computer, on the computer level. So there's two concepts you need to understand, which is when things are handled by reference or by value or by copy. If you assign a value to a variable and then you pass that variable along to a function or to another part of your code, the question is, are you actually moving the thing in the variable over or moving the variable over? And that's a very subtle distinction, and we'll try to make that clearer. And I'll pull up the Visual Studio Code, and I'll pull up some IPython and do some demonstrations here. Lists are handled by reference. When you define a list, and we call that L, for example, and then I pass L to, I do something with L, or I add to L or something like that, I reference the letter L, just the letter L. What I'm really referencing is a memory location inside the computer where L is stored, okay? And so if you make a copy of L, if you now say, okay, L is 5, 42, high, and M equals L, then M is not the same list, it's the same memory location to that list, okay? And again, this is a little bit confusing at first, and we'll do some demonstrations so you can see that, okay? That's a little different than numbers and strings, where those are passed by their value, meaning if I say S is the string high, and then I say T equals S, well now T doesn't point to a memory location, T just, you should think of as just having now the value high, okay? That gets especially tricky when we get into how functions receive data, and we'll get into that in a minute. Functions receive data always by making a copy of the data. But this gets particularly tricky in reference to the earlier stuff, because the copy, if it's a list, the copy of the list means I've copied the memory location where that list is located. So that makes lists mutable. And again, I'm throwing a lot of terms at you, and we'll go over this a little more slowly, okay? So the thing to remember is that lists are handled by reference, which means when you say L equals 5, 42, high, really all L is a memory location where 5, 42, and high are located. L, you shouldn't think of L as containing that list. You should think of L as only containing that memory location. As opposed to when you have a string or a number and you let those equal a variable, you should think of the variable there just psychologically. Don't think of those as memory locations, but the actual variable. S actually has the value high, as opposed to L, which has the value whatever this memory location is. This is a really striking phenomena when you start making copies of things. So let's do a little demonstration here. So let's see if I can change what I'm sharing to my VS Code window. Okay, there we go. Hopefully you all see that. All right, so let's do this. We'll say L equals 5, 42 high. 5, 42, high. Hope you can all see that. All right, so let's just take a look at it. Let's look at L. Okay, there it is. L is the list, 542 high. Now, that's what it's printing to the screen. Really, all L is it's a memory location. It's not 542 high. It's just the memory location where 542 high is located, right? So I can do my usual sort of thing. I can ask, what's L of 0? Oh, it's 5. Okay, no surprise there. All right, now let's make M equal to the list L. All right, so I didn't take the numbers 5, 42, and high and transfer them to L. All I did was whatever memory location L is pointing to. If L points to the memory location 42,534, now M points to the memory location 42,534. Okay, and 542 high is located at that memory location. So if I change the value of the first thing in M, let's just take a look at M, right? It's the same thing. But if I change the value of M0, if I make that 60, okay, well, no surprise, now M is 60, 42 high. But what is a surprise is if we look at L, we've changed the first value of L, okay? Because what we're doing is we're changing the thing located at a particular memory location, and both M and L point to the same memory location. Okay? That's very different than if I just look at something like x equals 3 y equals x. Okay, so now I can look at x. Well, it's 3. Y is 3. No surprise there. If I say, well, y now equals 5, well, now y is 5, but x is still 3. Okay, so this is just numbers and strings act very differently than lists. If I say x equals 3, y equals x, I've made a copy of the data and stored it in y. So now when I change y, I don't change x. Right? X is actually pointing to the data. It's not pointing to the memory location that points to the data. So it's a very different way of handling things when you're handling lists versus numbers. It's a really fundamental concept, and it can lead to lots and lots of bugs in your code if you don't understand this concept when you're working with lists. Okay, again, I've got my chat window up, so if anybody gets confused, please use the chat window or just turn your microphone on. I know this is kind of a new confusing concept. All right, let's go back to my iPad screen. Great. Okay. All right. So, I mean, that seems like it's bad, right? I mean, if I want M to be a copy of L and I change M, oh, now I've changed L. Okay, that seems super bad. So there's ways around that, which is called deep copy. So from the copy library, you just import everything. And one of the things you could import from that copy library is the deep copy command. So the deep copy command is in the copy library. So you import all the commands from the copy library, then you can use the deep copy command. And what the deep copy command does is it actually copies the data in L rather than its memory location. So at this point now, when you reassign the data to of M0 to 60, if you use the deep copy command, then it does not change the value of L. So that's one of the important concepts to worry about. Right? It's kind of an advanced programming concept, but it's important. There's a little comment here on the bottom, slicing is also deep. So I will mention this and I'll show you a little demonstration again. But this, okay, I'm doing this at the risk of possibly confusing you. Slicing is automatically creates a deep copy. So again, let's look at L here, L, okay. Now, let's say M is now L, oops, L of 0, 1. So M is just the first two things in L. What did I do? Oops, I wanted a colon there. M goes from 0 to 1. All right, so let's look at M. Look, there it is. M is, oh, I meant 0 to 2 if I want the first two things. Crap. See, I do these bugs too. Let's look at M. All right, good. Now M is the first two elements of L. So L was 60, 42 high. That's up here at the top of the screen. And M is the first two things in L, which is just 60 and 42, okay? Now I'm gonna change M. Let's say M of 0, let's set it back to 5. Okay, so now M is 542, no surprise, but L hasn't changed because when you do a list slice, it automatically does a deep copy. So you don't have to use the deep copy command, you can just use list slicing to create deep copies. Again, this, you know, when this is new to you, this is maybe confusing, but as you get used to it, it'll kind of sink in as you work with these concepts. I'll go back to my iPad screen if I can. There we go. All right, functions always pass by copy. So in other words, if I, whether or not it's a list or a variable or whatever, if I pass information into a function, then it creates a copy of that information. Okay, again, if I'm passing a list into a function, the information it's copying is a memory location. So that's, again, something you have to keep track of. But let's look here. This is a terrible graphic, by the way. I don't like this slide at all. There's something important about this slide, which is that FAV at the top is blue, and at the bottom it's black. You shouldn't think of those as the same things. The blue fav and the black fav are not the same. So first, let's look at what the conform function does. I input some value. So that whatever that is, if I say conform of 5, then FAV is automatically 5. Okay. Now I reassign whatever it was gets erased, and I reassign that to the number 42. And so now I'm going to return 42. So this function, all it does, no matter what thing I input, when I call conform anything 5, the answer will be 42. It'll just return 42. What's happening inside is that 5 gets stored here, okay? But then fav, the first thing the function does is it erases that 5 and puts a 42 there, and then it outputs the 42. All right, now let's see what happens when I combine that, when I use that function in other code. So we're gonna look down here at the bottom of the screen where it says def main over here, okay? So if I run the main function, the first thing that will happen is it'll print welcome to the screen, welcome. Okay, that's the first thing that happens. Then it assigns 7 to fav, right? That's what's happening here. Then it says fav is the output of the conform function, okay? So we take that 7, we put it into the conform function, so it goes all the way up here. The 7 goes in there, okay? But here's the point, is that functions always pass by copy, which means it's passing a copy of that 7. That blue fav is not the same as the black fav. So even though that blue fav now is going to get assigned the number 42, 42 will be output here. And then the original 7 is going to get assigned the number 42. It gets very confusing when you write some functions. So here, let's do another example. I think this slide is not the best illustration of what's going on here. So I'm going to go back to the code and let's do an example here. So here, let's say f, let's do something kind of mathy. F of x return x squared. Okay, so we could do f of 2. Oh, what did I do wrong? Oh, ha. X squared is star 2. Sorry, we're in Python. Okay, let's try that again. F of 2. F of 2 is 4, right? 2 squared is 4. Great. Okay, now let's say I do, I say x equals 7. Right, so now x is 7. And now I do f of 2. Okay. Well, f of 2 is still 4. Now that this may be still confusing to you, right? Because it looks from the beginning, from up here, it looks like what f does is it's going to assign 2 to x. Well, I just assigned 7 to x. Right? So look what I did in line 29 there down at the bottom. I assigned 7 to x. Then when I called the function, it looks like I assigned 2 to x. So you might think that now the value of x will be 2, okay? Now going down here, let's see what x is. Oh, it's still 7, right? And that's because the function just gets passed a copy. It doesn't change x, it creates a new x. It's not the same x anymore. It's just a temporary x to use internally within the function. And as soon as you leave the function, then you revert back to the old value of x. And that's this business in this slide of the old value of fab and the new value of fab looking like it was blue versus green, blue versus black there, is that when you call a function, the function that takes fab, you reassign the value of fab just internally within the function. And as soon as you hit that return statement and you get out of that function, then you go back to the old value of fab. Right? This isn't the best log to illustrate that. I hope that was clear from the thing. And you may have noticed that working with functions yourself. Okay, when you assign a function value to a variable within a function, it only works within that function. Right? The scope of that variable is what's called, computer scientists use the word scope. The scope of that variable is just within that function. As soon as you leave the function, you revert to the old value of the variable. All right? Where that gets confusing, we won't go through this quiz. Oh, by the way, I've been meaning to say this. I can download attendance data. Oh, somebody in the chat asked a question. Why would m equals l colon create a deep copy? That's just because the way the people who invented the Python programming language decided list slicing should work. They just decided list slicing should work by deep copy. And so they created Python so that it works that way. There's no, I'm not sure if that's an arbitrary decision or if they had some logic, some reasoning behind why they created it that way. It's a good question. All right. Excuse me. Lists are a little bit different. Lists are, oh, sorry, now I've lost my train of thought. I'm sorry. We were using quizzes to take attendance, and I said I would do attendance polls over Zoom, and I discovered after that that I can just pull the attendance data directly off Zoom. Once I log off of this, I can download a copy of everybody who was here. But attendance is, again, going to be fairly minimal part of your grade, so I wouldn't worry about it too much, especially if you're in a different time zone and you've notified me already, then I'll automatically give you credit for attendance. All right, let's get back to this slide. So this slide would be the quiz for today if we were there live. And I think let's just go through this so you can understand what's going on. So here, in the first one, let's do the first one here. So let's start at the bottom, right? So fab is 7. So we put 7 in the fab box. Then we call the conform function. So 7 goes right here, okay? Which means 7 is going to go here in this new blue fab. The blue fab is not the same as the black fab, okay? So just temporarily within the scope of that function, we're reassigning fab to 42 and then returning the number 42, okay? But as soon as we leave the function, we revert to the old value of fab. So conform fab, that'll give us 42, but we've left the function now, which means now we're in the black fab, which is just 7. Okay, that's a hard concept to understand. It gets very confusing, but I hope you're with me here. Functions create a copy, so you don't change the value of variables when you change them within a function. Okay? Lists, though, are different. The thing with a list is that we pass a memory location with lists, right? So function calls copies, okay? But lists are handled by reference. So this is where it gets a little confusing when you look at the two. So let's start with this second one. Let's call this main2 function. We say L is 7, 11. But really what L is it's this memory location. So when I call the conform2 function, really what I'm doing is I'm putting a memory location in here. I'm putting the memory location 42042. Okay, now let's go up to the top. So now we're changing the list at a particular memory location. Okay, now we're saying the fit L, which is the list at location 42042, is now 42, 42. So we've changed something at a particular memory location. And this L down here points to the same memory location. So this is 42, 42 now, because the function changed the thing at the memory location. Okay, so the word is mutable here. Lists are mutable. It's a question in the chat. In the first example, if you were to assign a variable to the output, then print that variable, would that print 42? Yes, it would. Yeah. If we said something like x equals conform fav, and we added a print x statement, then it would print out 42. Yeah. The last example here is the most complicated. L, again, is a memory location, okay? And what we've done is we've put a list at that memory location. That's what that line does. When you say L equals 7, 11, it puts a list at a memory location. Then we pass that memory location into the function. So it goes up here in the top, okay? Now we are changing the element 42 at a particular memory location, and we're making 42 the element at the second part. And I think, actually, I'm not completely sure. I think this does still do 42, 42, but I'm not sure because this L of 0 is technically list slicing, which creates a deep copy. Let's try it. I don't know the answer. So let's try it. Let's try it and we'll find out. I'm now thinking actually maybe it doesn't print 42, 42 because L of 0 is a deep copy of L. So let's just try it. Let's say def, I'll just type it in. Of L and L of 0 equals 42. L of 1 equals 42, and I'm seeing now there's no return statement, so let's just return L like in the previous examples. Okay, and now let's just go through the main function, just execute the steps there one at a time. In the main function, L equaled 7, 11. Now we call conform 3 of L, and the output's 42, 42 because I've returned this new list. But now let's see what L is. L is now 42, 42. So it did change it. It did change those things. So my guess actually was wrong. It happens. Actually, my original guess was correct. And then I was questioning myself, right? So 42, 42 is correct. It did change the things at that memory location. So it actually changed the list itself. All right. So that's this concept of mutability. When you pass a list into a function, you're really passing that memory location into the function. So if the function changes things at that memory location, then when you leave the function, they will be changed. So when you change something inside a function, those things, when you change a list inside a function, that list will be changed everywhere, which is different than if you just have a variable that represents a number. If you change that variable inside the function, then when you leave the function, you revert to the old value of the variable. Okay, I hope that's not too confusing. All right, so we're doing kind of 3 mini topics today. That's the end of the first topic. So as I said, if I have to leave this conversation a little early, Julie Medario has 3 videos for today's lecture, and that's the end of the first video. So I'll post this video now, and if I have to leave, then you can see hers as well. Okay, let's look at 2-dimensional data. This is a little bit of a review. I'm pretty sure we already did this. When we talked about the Mandelbrot set, we talked about how to store a whole grid of data when you're creating pictures or patterns. And we had a whole class day where we talked about this sort of thing. So this will be a bit of a review. again, if A is the list 42, 75, 70, then we can ask things like, what's the length of A? So length of A is obviously 3 there. This is a little bit more complicated. A is now a list of lists. We've seen lists of lists before. There are some questions here at the bottom that are worth thinking about. What's the length? Where is 3? What's the length of A? What's the length of A0? And how do you replace 10 with 42? And those answers are here on this slide. So the length of A, well, length, I'm sure we talked about this before, but in case you don't remember, the length of A is exactly the top level length. So it's a list of 3 lists. So the length of A will just be 3. 1, 2, 3. First element, second element, third element. Those numbers I just wrote on the top are not the indices of those elements. This would be element index 0, element index 1, element index 2. Okay, so A of 0 refers to this whole list, and A of 1 refers to this whole list. Right? Now, the next question is what is this 3? So I look at A of 0, and then I look at the index 2 element of A of 0, right? A of 0 is the list 1, 2, 3, 4. The number 3 is the index 2 element in that list, right? 0, 1, 2. And so that 3 is A of 0, 2. Okay, to look at the list, which is A of 0, and then the index 2 element. That 10 is A of 2 comma 3, right? It's the index 3 element, 0, 1, 2, 3. It's the index 3 element of the index 2 list. Okay, so A of 2 comma 3 is 10, and we can reassign that 10 with the number 42 just by saying A of 2, 3 equals 42. So we've replaced the 10 with the 42. All right, what's really common is to look at rectangular 2D data. We did this with the Mandelbrot set and some other image manipulation exercises that we did, where you have a list of lists and each of the sublists have the same length. And when you do that, you can think of the first index as the row and the second index as the column. So row 1, column 42 would be right here, right? That's row 0, row 1. Let me go back. I'm going to color code it. Row 0, row 1, row 2. Okay, and then next would be the column 0, column 1, column 2. So that 42 is row 1, column 2, which is why we're A of 1, 2. Okay, rows and columns. So again, you should just thinking of things as row and column will really help you keep track of your data for one of your next homework assignments. Now, if I want to step through all of the values in this list of lists, we've done this sort of thing before. We can use a nested for loop inside of a for loop. Sorry, my pen is, the color coding on there is covering up the stuff on the bottom, which is unfortunate. I guess I can change it like that. Okay. So what you see there is n rows is the number of rows, n columns is the number of columns. So when you say for r in range 0 to n rows, you're going to step through, r is going to be a variable that steps through the indices for the rows, and c will be a variable that steps through all the indices for the columns. And then you can do things with each row column element. So for example, you can change when the row equals the column, you can change the value to 4. And when the row doesn't equal the column, you can change the value to 2. So in this case up here, the row equals the column, so that'll become a 4, 4, 4, and everything else will be a 2. And we did this before, creating images this sort of way. And so again, this is just kind of a review, all right? Here's another thing you can do is the 2 in a row column data. So this is going to be really useful when you do your homework. In fact, when you do your homework, you're going to just mimic this code right here. So actually, let me give you a minute. I'll give you 2 minutes to stare at this code and see what it does. And the title of this slide is going to give you a big hint. Okay, to read this code, it took me 2-3 minutes to understand what this code did. And think for yourself in your own mind what B will be once you run this. Okay, I'm going to step aside for a second. You take a look at that. All right, let's see if you all got this right. So let's take a look at this. So again, this is a nested for loop, which means we're just going to go through all the rows and all the columns. Okay, R stands for row, C stands for column. Let's ignore this first condition over here first. Let's go to the elif command. So this is saying if A at a particular row and a particular column equals A at the same row but one more column, if they're equal, then we'll set the value of B to be true. So for instance, right over here, A at row 0, column 1 is the same at row 0, column 2. So that'll give us a true there at row 0, column 1. Now, same thing over here. We get a true. If that doesn't happen, we'll get a false. So we get a false here. And then we go to this column here. If we are in the last of the columns, then we'll just put a false automatically. So we can fill in the right side with falses. Okay, that's what that first if part is doing. Okay, and now let's see. Here we have 2 equals 2, so that gets a true. 2 does not equal 4, so that gets a false, but then 4 equals 4, so that gets a true. 2 does not equal 4, false. 4 does equal 4, true. 4 does not equal 2, false. Okay. So 2 in a row, all we're doing is checking with B whether or not we're 2 in a row, literally if there's 2 next to each other. So you can imagine now programming tic-tac-toe where you're looking at 3 in a row, okay? Now that would be one solution to tic-tac-toe. A tic-tac-toe board would be 3 in a row horizontally, but in tic-tac-toe, you also have to check for 3 in a row vertically and 3 in a row on a diagonal, okay? And that's exactly what you're going to program in your homework assignment. You're going to be looking at 2 in a row, but you want to check that diagonally and um, uh, vertically and horizontally and diagonally. Okay, so you're going to use this code as your starting point, but you have to think about how you would modify the code to do vertical checks and to do diagonal checks. Okay. This is all building up, by the way, to us eventually programming Connect 4. We're going to spend several days building up to Connect 4. Connect 4, you've got a vertical playing board, if you've never seen it, with little holes in it, and people drop checkers in from the top. And it's a little bit like a three-dimensional tic-tac-toe with gravity. It's like tic-tac-toe with gravity, where the two players have two different colored checkers, let's say X and O. And if um, there are 3 X's in a row, I think it's 4 in a row for Connect 4, yeah, Connect 4, obviously, then that player wins. And eventually we're going to work it to some basic artificial intelligence where we're going to program the computer to play Connect 4 against the user and trying to do that with some intelligence. And that's where we're going to get at by the end of the course. Before we can get into any of that, the computer has to be able to check, did someone win or not? When someone moved, either a player or the computer, is this a winning scenario? In which case we have to stop and say, player 1 won or player 2 won, right? So in order to check if somebody won, the computer has to recognize if you've got 4 in a row, right? This is a slightly easier example. Here we're checking, did we get 3 in a row? And again, you want to say horizontally, vertically, or diagonally. So you're going to program that as 3 separate functions. You're going to do a vertical check, a horizontal check, and there's actually 2 different diagonal checks you're going to do. And the way we're going to keep track of each of those functions are by using cardinal directions. North is up, just like on a map. That means east is to the right, west is to the left, south is to the bottom. So if you do the in a row 3 east, that's checking, do you have 3 in a row going eastward, checking just to the right, okay? So here, the answer will be yes, there's, so this is gonna take a couple of inputs. First, you need, one of the inputs is the checker. Do we have 3 in a row for player X, checker X? And where do we have 3 in a row? So if we start at row 0 and start at row 1 and column 0, and then look just to the east, do we see 3 X's in a row? Okay, and the list of lists that we're going to check is right over here. So we're checking list A. Here's list A. We're going to look at that. We're going to look at row 1, column 0. Okay, that's right here. And we're going to check the 3 to the right of that. So we're checking this one, and we're saying, do we see 3 in a row there or not? And if we do, we're going to output true. Okay. So we can do the other ones really quickly. So you're going to program 3 in a row, east, south, southeast. That's one of the diagonals. And, oops, and northeast, okay? It's the other diagonal. So I'll just do 1 or 2 of these with you since we are running, I guess we got about 20 minutes, but we still got to get to one other topic. So let's see, let's look at the next one. We're looking at row 1, column 4, row 1, column 4. Uh-oh. Let me pause this recording and take that. Let me resume recording. Okay, we're back here. And picking up here. So where were we? Oh yeah, we were at row 0, column 4. Row 0, column 4. And we're going to go to the south with checker O. So we want to go south with checker O and check 3 in a row. And we do, in fact, see 3 in a row there, so that would be true. And you can go through each of these. Hopefully you've been staring at the screen now for the last 5 minutes, so you've done this yourself. Let's move on. Okay, last little bit. So again, Julia Madero, if you want to go watch her videos, she broke this lecture up into 3, and this is the 3rd of the 3. And we've got about 15 minutes left here almost. It should be enough time to go through this. So this is your other homework assignment. This is actually technically the lab for this week. If we were still in class together, this would be the lab. Um, and again, this is an invention of John Conway. There's a picture of John Conway when he was a lot younger. He's just a total nut. So that's kind of a typical sort of pose for John Conway, him surrounded by a bunch of mathematical creations. Um, let's just go through the game of life. Yeah, and I'll show you just the XKCD cartoon for this week is relevant to this as well. So this particular lecture for this class is happening at a very relevant time given Conway's death. Um, Conway's game of life. This is an example of something called, now referred to as a cellular automata. Um, Stephen Wolfram, the guy who created the program Mathematica, is huge on cellular automata, and he even has a book where he thinks that it's the key to all life. And I think the study of cellular automata really started with this thing that was called Conway's game of life, something Conway invented. It's not really a game. It's a zero-player game. It's not even solitaire. It's not even a one-player game. It's a game only in the sense that you set up a starting configuration, and there and then things progress by definite predictable rules. So there are these rules, and it's almost like evolution. So the world is this grid of things, which again you're going to create just by creating a list of lists. And at every moment in time, some of the cells are considered alive, and some of the cells are considered dead. And the way you determine that there's a clock that's ticking, and the state of the board in the next tick depends on the state of the board right now. Okay, so here are the rules. There's really only two rules. That's it. Okay, so if you have exactly 3 neighbors, then that cell becomes live. And if you have an existing live cell, it will remain alive if it has 2 or 3 neighbors. And any other cell will die. Okay, so if it's dead, it stays dead. If it's live, it will stay dead. So let's look at some examples here. So for example, this cell right here, let's look at this cell right over here. It has 1, 2, 3 neighbors. Okay, and so that rule 1 comes into play, and it says in the next tick of the clock, that cell will now become alive because it has 3 neighbors. So we'll see that alive. Same with this cell down here. It has 1, 2, 3 neighbors. So it will suddenly become alive in the next tick of the clock. Okay, right? So now we'll see this sort of thing. Okay, now let's see what happens after this. So this cell now has 1, 2, 3 neighbors, so it will become alive. This cell has 1, 2, 3 neighbors, so it will become alive. Okay. This cell here has 3 neighbors, so it'll stay alive. This cell here has 3 neighbors, it'll stay alive. Same with this cell, same with this cell. But this cell here, this one over here, right here, it has 1, 2, 3, 4, 5 neighbors. 5 neighbors, and you die. Same with this one. So on the next tick of the clock, it looks like this. Okay, so again, we've started in this configuration, and then the next tick of the clock we're here, and the next tick of the clock we're here. So over time, it looks like these structures kind of evolve, and things can expand outward, and you can have everything just collapse and die and end up with a blank screen. You can have structures kind of propagate. It's amazing what happens here. So this one, for example, this cell will die. This cell right here will come alive. This one will stay alive. This stays alive. This stays alive. I'm not doing this right. 3 neighbors stay alive. 2 neighbors. Oh, sorry. This one dies. Let's look at this one because that one confused me. uh, this one here, let's look at this one. So you've got uh, 3 vertical bars. In the next tick of the clock, this one has 3 neighbors, so it will come alive. This will come alive. This will stay alive because it has 2 neighbors, but this one only has 1 neighbor, so it'll die, and this will die. So this vertical configuration will turn into this horizontal configuration. And then the same logic, that horizontal configuration will turn back into the vertical configuration. So what'll happen is this configuration alternates between vertical, horizontal, and you'll see it looks like it's flashing, flash, 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 okay? And so here are some nice examples, here's some little animations of things that will happen. So stable configurations, you've got these 4 blocks here, and they just stay 4 blocks. Then you've got these periodic configurations that'll alternate. And then there's more complicated things. This is called a glider. It self-propagates and actually moves across the screen. Same thing with this one here. You see the grid is moving slowly. Really what's happening is the grid stays stationary and the object itself moves slowly. I think that one on the right, on the bottom right, is called a spaceship. This one on the bottom left is called a glider. And Conway referred to these configurations that oscillate as plants and these things as rocks. And it really do start to get these different complicated configurations where everything's interacting with everything else. And if you just do a Google search for life simulations, Conway's life simulations, you can see some amazing configurations that create all things. People have created machines with like gears and like somehow arrange the little blocks to make like cars that move across the screen. And it's kind of shocking how much variation you can get. I'm going to do one more quick screen share before I go back to my iPad screen. One of my windows. Where is it? Safari. Let's try this. I don't know if you can all see any of that. Let's see. Oh, there it is. This was the XKCD cartoon for this week. XKCD, if I've shown you a cartoon in class, it's probably from the same author. It's a guy named Randall Munroe. He writes cartoons on at least a weekly basis. They're often have something to do with math or computer science or science. And you've seen a lot of his cartoons throughout the semester, and this was just put out a few days ago. It's a little tribute to John Conway, and incredibly sad again. And his tribute to John Conway was this game of life. And you could see, I think this is supposed to be an illustration of Conway sort of going off to heaven, but it's a nice illustration of this game of life where you start out with a stick figure and it turns into a glider over time and kind of migrates off to the top. And you'll see when you program this that you'll see a lot of behavior like this. Okay, let's move back to the iPad screen. Um, on the Harvey Mudd campus, there's a big plaza right in the center of campus, and you may have probably walked over this and not even realize what you were walking over. You could see it better if you look at the top view, and that is a still version of Conway's Game of Life. It's a big configuration that was it's a tribute to this particular game, partly because every single Harvey Mudd student takes CS5. And so every single Harvey Mudd student has had the experience of programming this particular game. And it's a really common programming assignment throughout computer science classes all across the country. I actually didn't take computer science in college, but I had a lot of roommates who did. And I remember them struggling with this particular assignment. Back then, the programming languages were not as easy as Python. I think this is easier to do in Python than in the languages that were around during that time. Here's some other nice configurations. This is called a glider gun. It's an amazing configuration someone discovered here. And as you let it evolve, it creates these little gliders that kind of shoot off to the side. This being just a close-up of one of those gliders. So you'll program this when you do the homework assignment tomorrow. that's it for today. Hey, my timing was good. Um, and if you have questions, let me know. Again, as a reminder, I have office hours tomorrow morning. I will try to make those. I will try to be in lab tomorrow afternoon. I did both yesterday. Only 2 people came to my office hours and 2 people were in lab, but I know you had a lot of time to do that assignment. You just be aware this particular assignment, actually the timing has worked out pretty well. I can give you some more time on tomorrow's assignment. Normally it would be due Thursday morning, but you have actually 3 assignments in your next, every other day you're only going to have one, but you've got 3 assignments this time. There's the 3 in a row functions, there's Conway's Game of Life, and then if you want, there's the extra credit, which is the Read It and Weep sequence. So I'll push back the due dates on those a little bit, just so you have a little bit of extra time since there are 3 of them to do. But your only chance to ask questions of me will be, um, I'll tell you what, I'll make it due right after my office hours Monday morning. So if you get a chance, if you don't get a chance to work on those tomorrow, then you'll be able to ask me Monday morning. Let's do that. Okay. All right. I'm going to sign off now. And hopefully I'll see most of you tomorrow or Monday, if not in class next Tuesday. Any quick last minute questions for the chat? No, I don't see anything. Okay. All right. I'll see you all later. Bye.